Good evening, everyone. Welcome back to the webinar series on quantum algorithms using Qniverse. Hello, am I audible? Okay, thank you for confirmation. Good evening, everyone. Welcome back to this week 2 of webinar series on quantum algorithm using Qniverse. On the previous week, we had with us Professor Apurva Patel from IASC. He touched upon two fundamental principles of quantum mechanics, that is factorization and superposition, which provides you the computational speed up over classical approach. He also touched upon Shor's algorithm and Grover's algorithm, which provides quadratic speed up over classical approach. So he also spoke upon quantum walk algorithm that can be used to solve NP complete problems with quadratic speedup. Today, this week, we have with us Mr. Henry Sukumar, who is the scientist F and group head for quantum technology group at C-DAC Bangalore. He is the brain behind the Quniverse development. So he brings him a vast experience of software stack development for various technologies like grid computing, cloud computing, and now quantum. With no further delays, let's hear from Mr. Henry Sukumar. Henry, over to you.
Thank you, Santosh. Am I audible? Yes, thanks for the confirmation. I got a confirmation from few participants. Let me share my screen. Hope my screen is also visible. Yeah. Thank you, Santosh, for a very brief introduction about me. So I also would like to thank Professor Apurva Patel, who was one of the key person in revolving what C-DAC is doing in quantum computing. He was a pioneer in teaching us in quantum computing. He brought us into the quantum projects through the QSIM initiative, right? So we should thank him first before I talk about the Qniverse platform. So before I speak about Quniverse platform, I would like to give a very brief introduction of the potential of quantum computing. You might have heard about the potential of quantum computing from Professor Apurva Patel. But I have some interesting slide here. So this particular slide, which I felt is very interesting, which I picked from McKinsey Quantum Use Cases report. If you look at this picture, it talks about the various stages of quantum computing, starting from the early stage and the late stage of noisy quantum computers. So we are in the era of noisy intermediate state quantum computers. And this is the state that we have few quantum computers available in the market. And this is what we have for trying out certain applications, right? And we are looking at the future where we will have a fully error-corrected quantum computers, which we will have sufficient amount of quality qubits that we can use for solving certain problems. And finally, we hope to have a universal quantum computer that can solve a lot of problems. Nevertheless, we are all sure and we are all very confident that the quantum computing has given a lot of value, and it shows the potential of solving problems that are not possible by the today's classical computing, even the high performance systems that we have. So here, if you look at some of the application area, we can look at some of the optimization problems in the field of traffic optimization. It can be in the financial optimization for the portfolio optimization, right? And these are the problems that will have an exponential growth, and that needs an exponential computation power where the quantum computing can benefit from. And then there are applications where we can develop the materials and we can develop new drugs, right? So quantum computers can be used for modeling molecules so that you can identify new drugs and materials. So these are some of the problems that can be developed using the quantum computing, right? So once we are sure that the quantum computing are potential in solving certain problems, what is the catch over here? We know that we can solve all these problems. We see that the technology is evolving. We see that there are multiple number of quantum modalities, qubit modalities, I would say, that are available in the market. There are leading players who are making the quantum computing as the future of computing. The way we are going to compute, the way we are going to communicate, these are going to be revolutionized, right? But there is a catch. If I say there is a catch, what is that? Now, if we have to make any breakthrough in developing these applications, right, by developing these use cases, then the challenge here is the algorithms, right? We need to develop algorithms, and developing these algorithms are not without any challenges. Particularly, it is very challenging for the algorithm developers and application developers, and also the users of quantum computing. So what are the various challenges that I see? Though you see multiple mountains here, it is not in any specific order. But what I'm trying to bring out here is, at present, if there is a user who wants to develop a new drug, he wants to do a molecular modeling and develop a new drug, then what is the challenge that is presented in front of him? If you ask him, there are multiple qubit technologies that exist in the market, right? For example, let us say I am a researcher who wants to develop a new drug. Then I see there is a company which is developing a superconducting based quantum system. There is a company called IBM who has superconducting based quantum systems. There is a company called Rigetti who again work on superconducting systems. There is a company called Xanadu which works on photonics based quantum computers. And again, there is a company called Pascal which works on neutral atoms. And these qubit modalities does not end with these three. We can still talk about NV center based quantum systems, ion trap based quantum systems. We can talk about quantum dots, and Microsoft is talking about topological qubits. So there are multiple qubit technologies that exist in front of a user. And here the problem lies. I am not sure which is the qubit technology that I have to adapt for solving my particular problem. And each of these technologies come up with their own SDK frameworks, and they have their own libraries for writing their programs, right? So Qiskit can be used for connecting with IBM superconducting system, and Rigetti has a PyQuil SDK for connecting to their system. And there is a separate set of library called Pascal for connecting neutral atom systems, right? So there is a fragmented ecosystem at present, and there is no a unified standard that exists, right? As an application developer, I am not really bothered where my algorithm is going to run, how my problem is being solved. But what I'm worried is how do this. Okay, so I'm just worried I need an interface, a standard interface where I can put my problem, I can give the inputs to my problem, and I would like to get it solved by any of the computer. I'm least bothered about the complexity behind that, right? And the other big challenge that I see here is the interoperability, right? The quantum computers, they don't very well interact with the classical systems, right? When we talk about hybrid applications, so how well an application that has the potential of you making use of a classical system and the potential of making use of a quantum system, is there a library that can split these things, these application into two different modalities, and it can run and benefit from these two technologies, right? So there are few standardization agencies, like including IEEE and some European standardization groups who are working on these standards. But still, this interoperability, there is a big challenge. So we wanted to bring that challenge to be addressed in the Quniverse platform. And then look at the learning curve of the quantum mechanics and quantum computing, right? Understanding the quantum mechanics is very challenging, and particularly if you are from a different background, from a computer science or from electronics or any other domain, non-physics or quantum domain, then you are going to have a challenge in understanding the quantum mechanics. So we need to have a platform that actually lets the beginner to make use of this platform to understand how the quantum mechanics is working, what are the principle behind that, and how they can write their quantum algorithms, right? So these are the various challenges that I would see for an algorithm developer and user. So that's the reason we ran a survey. Okay, we wanted to find out whether the users also have are feeling the similar challenges, right? So we ran few questions. We ran it for a week or so, and then we had around 200 participants who had participated in the survey. And if you see the first question, what are the computing frameworks that you are currently familiar with? 57% of people felt that Qiskit is the one to go for. And then there are other frameworks which I can see is few percentages. And then there is another question which we ask: do you need a unified platform that integrates all these quantum technologies, right? And interestingly, the 78% of people say that we need a unified interface, and that is what the Qniverse is trying to provide. And the other big challenge, if you see, what are the challenges that you face when you are trying to learn quantum computing, or when you try to develop an algorithm? When we asked, you can see on the leftmost bottom picture, they say that the knowledge sharing and the resources that are available on quantum is one of the biggest challenges. 26% of people felt that this kind of a platform is required. And they also felt, 15% of people felt that there is a constraint in using the hardware, right? If you go to access an IBM hardware, definitely you have to pay a lot of money over there. And IBM Cloud does not support right now the simulation frameworks, which once they were supporting, and we were using those for simulating some of these algorithms. Now we have only the hardware available over there. So these are the pretty important problems that needs to be addressed, and this motivated us to develop a unified computing platform, and that is what we are going to see as Qniverse, and that is what you're going to learn in next few weeks on various algorithms that will be demonstrated using the Qniverse platform, right? So this particular quote, I like it very much, from Winston Churchill. He says that out of intense complexities, intense simplicities emerge. So these are the complexities that I was talking about. There are multiple challenges. There are multiple qubit modalities that exist in the market, and there is a lot of complexities involved in quantum computing. And that is what gave us an opportunity to come up with a very simplified platform that is called as a Qniverse, right? So Qniverse is an integrated platform that allows users to design, simulate, and execute quantum algorithms on classical accelerators. When I mean, you can run these simulations on CPUs, and you can also run these simulations on classical accelerators such as GPUs, FPGA, and vector processors. And the same code that used for running on these simulation frameworks can be run onto the quantum hardware. So it means that you write one code, and this code is compatible to run on any simulation framework that exists in the market, be it a Qiskit or Cirq or Penny or Quest or QLAX or CUDA Quantum. We take care, this platform takes care of translating this particular quantum circuit into the respective simulation frameworks, and the same code can be used to run on a superconducting based system, and you can also run them on ion trap based system. At present in Qniverse, we have superconducting system and we have ion trap system. The next versions of Qniverse, you will definitely see the photonic systems and neutral atom systems getting integrated into it. Okay. At the heart of Qniverse is the quantum software development kit, which is actually providing all the features that you're going to enjoy with the Qniverse, right? The libraries, the interfaces, the building blocks, and the various optimized quantum algorithms. All of these are provided by the Quantum SDK, and that sits behind the Qniverse interface that you're going to see, right? So this is the basic architecture of Qniverse. So you start with the Qniverse platform, which will look like, which is basically a web application. And you will have a platform where you can design your quantum circuits. Once you have your quantum circuits created, this visibly created quantum circuit is then translated into an quantum intermediate representation, which we call it as a QASM, quantum assembly language. And there is an integrated transpiler which takes this QASM as an input, and then it converts them into any of the simulation framework that you wish to code in, right? So you can convert them into Qiskit or convert them into Cirq or CUDA Quantum, and you can start simulating them. And behind that, there is a bit of an optimization and set of hardware constraints that are handled in order to run them onto the simulators and onto the hardware platforms. So when you want to run it onto a simulator, these simulators are ported onto the high performance systems that we have in C-DAC Bangalore. We have a PARAM Utkarsh HPC system, which is close to 1.6 petaflop performance. And that has the GPUs, vectors, and FPGA cards. Right now in Qniverse platform, you should be able to use CPU and GPU. The next versions, you will see the vector and FPGA platforms, which will be given by some of our team members from C-DAC Pune and C-DAC Noida, right? And to integrate with the hardware, we have two different approaches. We work with the cloud API to integrate with the different types of quantum computers, including the superconducting system and photonic systems. And under the superconducting system, we have IBM quantum system installed, but unfortunately for last 1 month, we have there is a change in the way the IBM APIs are being accessed. So we have a little bit of downtime on the IBM quantum computer, but we have ensured that we still get IBM quantum computers from a third-party API called SuperStack. So you will be able to access IBM quantum computers. And we are working with a Delft company, which is called as Quantum Inspire, where they have a spin qubit and then superconducting qubit, a Starman 7 and 203 5-qubit machines. So those machines will be coming in the future. That is why you see it as a green block, which is for the next release. And the one that you see in the orange, the platform is future ready. And this can be integrated with the future developments in National Quantum Mission and also with the superconducting machine that we are setting up in C-DAC Bangalore, a 100-qubit machine, which is called as a quantum reference facility. So that will also be put into the Quniverse platform. So in few months down the line, the users who are joined here, you will be able to make use of many hardwares that are available in the market, right? So this particular slide talks about the very important features of Qniverse. As I was explaining, it is an unified interface. So you don't require to write a code for accessing a particular qubit hardware. You can write once and use that for any quantum hardware. And as I was explaining, it is platform agnostic. You write one code which can be simulated onto a classical accelerators and also on the quantum hardware. And behind that is the quantum SDK. We spoke about it, and we already have a lot of algorithms, and each of the algorithms that have been ported into the Qniverse platform is the one that you will be learning in the coming weeks, right? So we'll be touching upon each algorithm separately, and the people who develop those algorithms and the people who optimize those algorithms are the ones who will be delivering the talks to you, right? And then, as I was explaining that we always, C-DAC has been considered as the supercomputing people. So we are the high performance computing people. We have experience in deploying HPC systems across the nation, right? So we always see quantum computers as an accelerator. And we strongly believe, even Professor Apurva Patel keeps saying that, let the HPC systems or the classical systems do the job that they are good at. Let the quantum computer be used for the problems that the classical computers cannot solve, right? So when you need an exponential computational power, you go for quantum systems. Otherwise, we feel that both the system has to coexist and they have to be interconnected so that we can solve some good problems that can be addressed for the nation, right? So hybrid classical quantum workflow has been integrated into this platform. I think there will be a session on variational quantum eigensolvers, which is basically a hybrid application. I strongly feel that a meaningful quantum application will always be a hybrid application. And you will have a demonstration on VQU-based systems, which very well you can use on Qniverse platform. And Qniverse platform can be a very good tool for the education purpose. So we have been already It has been already used by some of the institutes like Amrita University, Chennai, and then Manipal universities. They have been using it for various training programs. And C-DAC have been particularly using this platform for various FTP programs and workshops, right? So why Qniverse matters? As an application developer, it actually provides you with the entire life cycle of quantum algorithm development, starting from designing the circuits and validating your circuits with the existing simulators in the market, optimize your circuits and run those circuits onto an quantum hardware and visualize your output. So you get the complete life cycle through this platform. So that's why it gives you a less time in developing, and it provides a simplified access. So I need not roam around the market, choose different platforms for accessing different hardware. Everything has been put into one interface, right? And we also have a best way of debugging your programs, right? So I will be demonstrating how you can debug your programs using the Qniverse platform, and the portability code ones run it onto multiple accelerators and as well as hardware, and it can also accelerate your learning curve. So with this, I will end my presentation, and then we'll get into the demonstration of Qniverse. So Qniverse ultimately was aimed to balance the performance and accessibility, enabling the users from diverse backgrounds to engage with quantum computing effortlessly. The place which I have circled, which is the diverse background. So even if you are from a different domain, which is non-quantum domain or non-physical physics domain, you should be able to use Qniverse without much hiccup. So with this, I will get into the demonstration of Qniverse. I hope my browser is visible, right? My browser is not visible. Okay. It is visible. Okay. Yeah. So in order to access Qniverse, I think I have already seen many people taking an account from Qniverse. Good luck to you guys. And I'm very happy to see we already have around 4,000 users who have registered for Qniverse. But please don't log into Qniverse right now because I'm going to demonstrate. Let us do that later on. You will get a chance to try out the Qniverse platform later on, but let us focus on this demonstration right now. So you can log into Qniverse. Those who don't have an account, we have enabled a registration link where you can just input few basic information, where you can talk about what is the research that you would like to do, what you expect from this particular platform, and validate your email address, and you're good to go with the Qniverse platform, right? The front page that you see is basically, I would say, as a marketing page. We talk about what is this platform is all about. What are the various features that it offers, basically what you saw in my presentation. And then there is a video which beautifully explains the benefits of Qniverse platform and what are the various hardware that you can see. Don't get fooled by what you see here. We don't have a photonics hardware right now, but definitely it will be there in the platform in next coming weeks. And then we also have some of the FAQ, which is most frequently asked by some of our users. So those get answered over here, right? So straight away, let us log into this platform and see how it can benefit your quantum education. So all you need to do is we have a secure login page, input your username and password that you have created during the registration. And then you get this platform here. So this is how the platform looks. I briefly take you through the platform. So you see a drag and drop interface. If you can see my mouse moving around. So this is a drag and drop interface where there is a gate palette. So we have grouped these gates as single qubit gates as one palette, and then multi-qubit gates, and then measurement gates as one palette. And then we have certain building blocks. For example, QFT building block and inverse QFT building blocks are available, right? And the below place where you see is the, maybe you can call it as a workbench, or you can call it as a composer, where you can drag and drop the quantum gates, right? The moment you drag and drop your quantum gate, for example, I have dragged and dropped a quantum gate onto the composer, which has 3 quantum registers and 3 classical registers. And once I drop this gate, you can also see on the right side, there is a code editor. So if you look at my presentation, I was explaining about you can build your quantum circuit visually. Once you build that, we translate that into an quantum intermediate representation, which we call it as a quantum So QASM, which is quantum assembly language. So that is what you see here. So the moment I drag and drop a particular gate, I see that the corresponding code, the QASM code that gets generated automatically. And you can also start writing your own code as well. Okay, and this editor has been beautifully designed so that if there are any syntax error, you will get notified that. So you can fix your problems, and then you can see that whatever you write over here, it gets translated to the visual thing, right? And there is an integrated transpiler, which basically takes this QASM code as an input, and I can see what is the corresponding Qiskit code. So you need not write a Qiskit code. So you don't need to spend a time. You are an algorithm developer. You need to focus on your particular problem. So you shouldn't be wasting time in doing these translations. That is the aim of Qniverse. So you get your code translated by a click of a button. So you translate it into a Google Cirq format. So tomorrow you want to run the same code onto a Google's quantum computer. You straight away copy this code, and your code, you are good to go run it on Google system. Similarly, you want to run it on NVIDIA GPUs. So we have a CUDA Q library integrated, which translates your QASM code into CUDA Q format, and you can straight away run it on a GPU platform. Similarly, there are two very recent simulators that we have integrated, which is called Quest and QLAX. They basically provide you with the ability to run up to 40 qubits, right? Which you cannot get with the other simulation frameworks. And let us assume that you are a very good coder and you would like to improve the code that we provide with the Visual Builder. You wanted to get into the coding. So there is a Qiskit editable version, and you can start editing your code over here. So you can write your entire algorithm over here and submit that algorithm onto the platform, right? So there is some interesting widgets at the bottom. You can choose to close or keep it open, but I would recommend to keep it open, right? So let me explain that. For example, I can delete this gate by clicking on them and then click on the delete icon. So we have a Hadamard gate over here. So what does it mean? That I have a Hadamard gate which is placed on qubit 0. It means that I want the qubit 0 to be in superposition state. So it means that this Hadamard gate places the qubit 0 in equal superposition of 0 and 1. For understanding purpose, let us have only single qubit. So I can just click on manage link, and then I go to this, and I have one quantum register and then one classical register. And you can see that the qubit, which starts with initial state 0, and the moment I place a Hadamard gate, it places the qubit 0 in equal superposition. So it means that 50% of time it is in state 0, and another 50% it is in state 1, right? So let us also see the state vector representation of it, right? The state vector does not basically, the probability distribution does not basically show the phase distribution. So you can make use of state vector representation, which will show the phase distribution. For example, there is a widget over here, which is basically a help widget. So we are talking about Hadamard, so let's keep Hadamard. And on the Z basis, which is a 0, 1 as an input. So when I give an input 0, it gives me an equal superposition of 0 and 1. But when I give an input 1, right, when I have a qubit with an input 1, so it places, it gives me the phase distribution. So we can basically have a NOT gate placed over here, and then you get to see the phase distribution. So basically a qubit is getting rotated, and you see the rotation of the qubit, which is as a phase angle here, 180 degrees, that is being shown over here. So that is how the state vector representation can help you in various instant understanding, right? And the probability distribution that you see here is basically an idealistic distribution. It means that it does not talk about the noise parameters, right? We are not actually simulating it, but we are showing it instantly what is the idealistic probability distribution when I have a particular gate over here. So I have a NOT gate over here on a qubit 0, which means that I start with the state 0 and I have a NOT. So I expect it to be in the state 1. So you see, you have to read this from the left side. For example, 1 represents the qubit 0 and 0 represents the qubit 1. So now, probably if I have one qubit, that is more explanatory. Yes. So now you see that the qubit has been flipped from state 0 to 1, right? And what if I want to initialize my qubit in a different state? So you just need to click on the qubit. And here, I think Dr. Naresh will be speaking about this in the coming session. We are planning for one intermediate course session between this Wednesday to next Wednesday, probably on Monday. I think Santosh will give an input on that. So when Naresh speaks about it, he will be speaking the mathematical representation of qubit and how you can initialize those qubits. For now, understanding purpose, I'm just going to set this qubit to a 1 state, right? So you can see the color coding here. The Q0 is represented in red, which means that now the qubit starts with state 1, and I have a not place. It means that the probability distribution should be 1. So 100% it should be in 1. So this is the idealistic probability distribution that you can see, right? So let us switch it back to state 0. Okay, so we have state 0 now. Let us have a couple of qubits on the register. So now we'll try to create an entangled state, a bell state, right? So I will place a Hadamard gate here. Then I place a 2-qubit operation, which is called as a C0 gate. C0 gate basically will work with more than one qubit. So it means that there is a control qubit where you see the dot operator, and there is a target qubit where you see the not operator, right? So the control qubit will actually instruct the target qubit to change its states based on the input it receives, okay? So if the control qubit is state 1, then I expect the target qubit to do a flip operation. Okay, if the control qubit is state 0, then I do nothing on the target qubit. So that's what we mean. Hence, we have a Hadamard gate placed over here. It means that the qubit at the end of a Hadamard gate can be in the equal superposition of 0 or 1. So what is the probability that we can expect is the qubit 0 can be in 0 or 1 at any point of time, right? When it is 0, it actually does nothing on qubit 1. When it is 1, it actually does a flip operation. So probable states that we can get is 0, 0 and 1, 1, right? So this is an interesting operation that we do with entanglement. And entanglement has plenty of applications in quantum computing and as well as in quantum communication. You will definitely learn about all these things when we are talking about the algorithms in detail, right? So this is the basics of creating the qubits, creating and manipulating the qubits with various gate operations, right? Before we talk about the details of this, you can see on the rightmost side the list of jobs that I have submitted and what are the various states of this particular job. You can click on the particular job and you can load those outputs. So this is the job that I tested before coming for this session. So I submitted an entangled state, a bell state, right, with 2 qubits. And you see that the probability of those possible states 1, 1 and 0, 0, which is being shown over here. And you will also see if there are any errors in the circuit. So this way you get to know that you have made some errors in the program. You can go back, you can load those circuit back, and you can edit those circuit and correct your mistakes, okay? And you'll also see the Quantum code that was used for submitting your simulation and how your code has been transpiled, right? So we submitted, I submitted onto a Qiskit state vector simulator, Quantum simulator. So this is the code that was used, right? And there are some pretty interesting statistics which helps you to know how your job was in the queue and how long it was in the queue and how long it took to execute, right? And what is the current state of it and which platform was used for the execution, whether it is a CPU or GPU or any QPU platform, right? So before that, I would like to show this particular page, which might be an interest of you. This is the compute resources page, which shows, which give a glimpse of what are the various simulators that is supported in the Quniverse platform. For example, as I was explaining, we support Qiskit simulator, and Qiskit simulator comes with a bunch of backends, right? If you have heard about Qiskit's AIR package, it supports state vector simulators, density matrix simulators, Quantum simulators, and MPS simulators. Basically, each of these simulators are meant for different purposes and specific purposes. So when you want to deal with a quantum systems, which only deals with the pure states, right? You deal with a quantum system that does not interact with the environment, which does not have a noise, which is very an idealistic quantum state. Then you generally use a state vector simulator, right? For representing those circuits into a state vector, and then you simulate them. State vector has certain advantages. They are less compute intensive, but whereas the density matrix simulators, which can work with a quantum state with pure states and as well as the mixed states. It means when I say the mixed states, a quantum computer is basically there is a flow how it works. It's an ecosystem that has a dilution refrigerator where you have a beautiful chandelier where the qubits wirings are then. At the bottom of the dilution refrigerator, you have the heart of the quantum computer, which is the quantum processing unit. And then you have a control electronics, which is made up of some microwave signal generators, arbitrary waveform generators. These actually generates certain pulse and waveforms to interact with your quantum processors. And then you will also have cryogenic electronics, which are called as an amplifiers, which will be part of the dilution refrigerator. And then finally, you have a platform like a Qniverse, which you use from the classical systems, right? Now, when I talked about a control electronics, any qubit operation that you performed, for example, we had a simple circuit where we placed a Hadamard gate, and then we were manipulating these qubits, right? And each of these qubits are nothing but a pulse, which is generated by a control electronics. And each of the quantum gates that you create, be it a Hadamard gate or NOT gate or a multi-qubit gate, all of these gates are again finally a piece of an electronics which helps in generating these pulses, right? So these electronics cannot be perfect. You cannot expect the electronics to be always perfect, and these electronics can have noises, right? So that is where your qubit or your quantum circuit becomes noisy, right? So you wanted to run a problem and you wanted to get a desired result, but these noise are going to be a villains for you, right? It's going to play a major role in affecting the way these problems are being solved. So it can interrupt your quantum operation. It can, for example, when I place a Hadamard gate, what I mean is I wanted to rotate my qubit from a particular state to a superposition state, right? So this rotation operation is performed by a particular pulse. And if this pulse is not 100% perfect, even if it is only 99.9% perfect, there is a bit of an error over here. And this error will not give you 100% desired result, right? So this is how the noise is going to affect. And density matrix simulator is something that helps you to deal with such noisy quantum simulations, right? So each of the simulators that you see here is meant for a specific reason, a specific purpose, okay? You will get to understand which simulator that you should use in the coming sessions when we are talking about the algorithms, right? Right now, Qniverse does not have a noise modeling, but it is not very far from having it. Probably in the next version, I think we will have a noise modeling where you will deal with these simulators. And as I was explaining, there are simulators which can run on the GPU platforms. These simulators are optimized to make use of the parallel processing capabilities that these accelerators provides to you. So right now we have a GPU simulator, but definitely we will have an FPGA simulator and vector cards as well. So these accelerators can solve certain problems much faster than the traditional CPUs and GPUs does, right? An interesting part that you will be like to see is the quantum computer. So we have IBM's Brisbane quantum computer. What you see here is a 127 qubit quantum computer, and it gives a pretty good information like what is the maximum number of shots that you can run on a quantum computer. So if you ask me what is these shots, right? When I run a particular problem on a quantum simulator or onto a quantum system, right? If you run it once, the quantum is going to give you a probabilistic output. Okay, so one run is not enough to come with an ideal probabilistic understanding of a particular problem. So what we do is you run these simulations n number of times. Probably in a layman term, I can say you can call it as a number of executions, right? But that is a max terms, max shots that is used by some quantum computing systems, right? So if you run it for 1 lakh shots, it means that you are trying to run the simulation for 1 lakh number of times, and then you're trying to get the ideal desired result, right? So we have computers from IBM, which is located in various other locations, and we have 127 qubit and 156 qubit system. And this is where C-DAC Bangalore's quantum reference facility, which will be close to 100 qubit, will also be available in next 9 months time. And interesting part here is we are talking about a superconducting system. But there are two main players who are deal with superconducting system. One is IBM and other one is Rigetti. So we have Rigetti's Anka machine, which supports 82 qubits. And what are the list of gates that are supported by the Rigetti system? So this is an interesting page that you can have a look at later on. But in order to list these QPU informations, you will have to go to your profile page. Okay, there are two sections here. One is to generate your IBM key. I think there is a help which you can click here and learn how to generate an IBM key and input your IBM key over here so that you will be able to submit your simulations onto an IBM system. Similarly, SuperStack is another third-party API which provides us even the IonQ system. We should have an IonQ system today. It was there in the morning. Probably it is down right now. So I'm not able to see in the listing today. But anyway, if you're lucky, you should be able to see it in the coming days, right? So you just need to generate based on the guide that is given here and input over here and save your profile. Simple as that, right? And then there is an algorithms page where we have almost, these are the popular algorithms. These algorithms, definitely C-DAC did not develop these algorithms. These algorithms, you will find it in the internet. You go to Qiskit library page or a documentation page, you will see these algorithms. But there are a few set of algorithms which C-DAC has developed or C-DAC has modified. And we have an algorithm from a professor called Anirban Pathak from JP Institute, who has developed a quantum veto protocol. So we have that. So if you are a very good algorithm developer and if you are listening to my talk or if you are planning to use Quniverse, you are welcome to develop algorithms and share it with the community. All you need to do is just write a mail to us and we will include your algorithm here, and we'll also mention or give a credit to you, your publication or whatever it is, right? So we will probably see one example. I will not get into the details of these algorithms because we are going to have a separate session for each of these algorithms. That's why it's a 14-week long. So let us say that we wanted to deal with a Grover's algorithm, which is a famous search algorithm, right? So I will say that I wanted to have a winning state of 101 with 3 qubits. And I just click here. You need not develop your oracles by hand. The oracles get generated automatically. So what you see here are the barriers, right, which splits the circuit into various sections. The first part that you see is I have a 3 qubit and I have placed all the 3 qubit in an equal superposition, right? So I have placed a Hadamard gate over there. And then I have the next section where this particular section, which I am highlighting, is called as an oracle. And then the next section is called as a diffusion operator, right? So this oracle is dynamically generated based on the input that I have provided. For example, I gave an input as 101. And this oracle's job is to say that whether this element is present or not, yes or no, as simple as that. But if you're developing a Grover's algorithm with a different input, you will have to sit and develop these gates that builds this oracle. But in Quniverse, it gets automatically generated. So that's the advantage of Quniverse, right? And then this is the diffusion operator section that you can see. And what is the, what is the instant probability even before I run the simulator onto any simulation framework or hardware. So I gave a winning probability of winning state as 101, and it says that 94.53% of probability that I can get this winning state, right? And then you see the iterations of the oracle and diffusions, because we are dealing with possible states, because we are dealing with 3 qubits. So we need to have 2 iterations to do that. I think this will be explained in detail by my colleague, Mr. Raja Singh, in the future session, right? Now, the one interesting feature that I would like to show to you is the grouping of gates, right? What I need to do is I can just select this set of gates, okay? And I can click on this particular icon. I just need to give a custom gate some name. I can call it as a custom gate. I save that. And all the custom gates that I have created over here, it gets saved in this particular place. So this is for saving the custom gate and as well as some of the building blocks that we have, right? And then I can also group this. Probably I should have named it with a meaningful thing. This is the diffusion operator. Diffusion operator, right? I will save it over here, right? And there are multiple iterations. So now I will select all these things. I will delete it, including this. I will delete it. Okay, and I just need to have the diffusion operators 2 times. So I have the Oracle operator and I have diffusion operator. So you can see that this platform does not only allow you to develop larger circuits, it gives you enough scope for you to group these gates. So even the complex gates can be grouped Yeah, I just need to select, and you can see what are the set of gates that is used for building this particular custom gate, right? So you get a lot of space to develop a larger algorithm. So that's the idea behind it. Finally, you can also group these 2 things and call it as a Grover's operator. And if you're using this Grover's operator in any of your quantum application, all you need to do is just drag and drop over here. It's simple as that, right? So I will remove all these things. And one thing that I forgot to explain is the QFT building block, right? Quantum Fourier transform is something that you would have heard about it. It has plenty of applications. We use it in Shor's algorithm. We use it in various optimization algorithms and simulation algorithms, right? So Shor's plays a key role, and you need not build a Shor's gate from scratch. So sorry, QFT gate from scratch. So these are the set of gates that helps you to build a QFT, right? And we also need sometimes the inverse QFT. In some applications, you wanted to have inverse QFT operations. You just need to drag and drop that onto this palette. Simple as that, right? So these are the things that you can do with Qniverse. Did I miss something? Yeah. Yes. The other thing is we haven't submitted the job. Maybe let us submit one job. So I will have an entanglement circuit created. I just need 2 qubits. So let us just have 2 qubits. Finally, I need to measure these qubits. So I will measure these qubits. Okay. So here you see the idealistic distribution. The states, probable states that I'm expected to get is 0, 0 and 1, 1. But let us see that by running the simulation, right? I can choose what I wanted to do with, whether I wanted to use it with Qiskit or use it with Cirq. But let us keep Quasum as of now and click on this run button. So here you see some interesting features, like I can run it on, I can choose to run it on CPU or on a GPU, right? And vector is something, as I told, it will come in the later point. And I can select CPU and I can choose the list of simulation backends that I showed you in the compute resources, right? Let us keep it as a Quasum simulator and click submit button. So what you see here is this simulation is submitted to a resource manager, which we call it as a slurm that runs on a high performance system. It takes your input, it assigns you a job ID, and then you get to see what is the status of your job here. Just click on that. You go to a page where you can see the output of it and what is the current state of that particular job. So when I click a refresh button, probably if the job is completed, yes, it has completed. And you can see that the idealistic distribution was exactly 50% for the states 0, 0 and 1, 1. But when I ran the simulation, right? So I ran it for a particular number of shots. By default, it is 1024 shots, I believe, right? You can also customize that to 2048 shots as well. But by default, it is 1024 shots. So when I ran it, I see that the 0, 0 state has 51.66 percentage of probability, and the other one has 48 percentage of probability, right? And this is the circuit that was used, and this is the time it took to run on the HPC system, right? If you want to modify this algorithm, all you need to do is just click on load circuit and that gets loaded. You start adding more gates. It's simple. You can keep developing your algorithms. So now you use the simulator. You have validated your output by running it on your simulator. So you are able to validate your algorithm with the set of simulators that we have, right? Now you can also click on this and choose to run it onto a hardware. So when I was talking about a hardware, the hardware need not be perfect. We are talking about a hardware that are available in the NISQ era, noisy intermediate quantum systems. So in this era, these systems are expected to be noisy and they are expected to have errors, right? So when I run here, I don't see that they can give me a desired result, but they can take me to a closest result based on the noise that they are getting affected with. So I choose a Rigetti system and I submit the job here. If the Rigetti system is available for me, I'm lucky that I have the job ID presented to me here. We'll just click here and you see that the job has already completed. And you can see the difference in the probability distribution here, right? We see 0, 0 and 0, 1, 1, the same output, but there is a difference in the probability distribution. And it was run on the Rigetti system. So you have your algorithms validated with the simulators, and then it is ready to go onto a real quantum hardware. So that's the benefit of Qniverse, right? Then, thank you, Raja Singh, for reminding me that there is an interesting chatbot. So we are in the world of AI. We cannot definitely miss out on AI. So any tool that we develop has to be integrated with AI. So we can ask some basic questions. What is quantum computing, right? So instead of going to ChatGPT and Gemini, which most of us do all these days, you get that integrated into this platform with the Q Assist feature, and it explains what is quantum computing is, right? And it also suggests the various questions that you can further ask to this Q Assist. Interestingly, this Q Assist is faster because we are running it onto our GPU platform, right? So we have done a lot of parallelizing operations so that even if there are multiple users trying to query this Q Assist, it gets done the job. It does the job pretty faster, right? Another interesting thing which hint that my colleague Raja Singh told is, what was that? Tell me the status. Tell me about my last job, right? So when I give this query, it actually says that my last job was submitted and this is the job ID. It was ran here and what is the state where it was run. It ran on Rigetti's quantum system. And I can also say that tell my last job that was run on GPU. So it will try to fetch the most recent job that I have ran on the GPU platform with the job ID as 5658 and what is the job ID. And it was run on the Qiskit environment using GPU acceleration and it took 2 seconds to run. So there are pretty interesting features that you can leave it. I will give a freedom for you guys to explore this platform and try out this Q Assist. And if you have any feedback, you can let us know. And the other important thing that I would definitely say is we have a pretty good list of documentation that is available. We are trying to improve this documentation so that you will benefit out of this. So what we have here is the various algorithms, how the QSDK, that is the brain of this Quniverse, is actually working. And there is also bite-sized videos which explains, I'm not able to track it here, maybe quantum algorithm section that is inside QSDK, probably. Yeah, algorithms here. So Simon's algorithm. No, yeah. So there is a bite-sized video which actually explains how you can load Simon's algorithm into Quniverse platform, how you can play with it, right? So there is a video for every algorithm that we have, right? So we explore this. And yes, the credit system, right? So as I was explaining, when we ran the poll, we understand that it is very important for C-DAC being a government organization. We'll have to be a very responsible individuals where we need to develop a platform that will help our citizens. It will help our nation to grow together in the quantum computing, right? So you will all agree uniformly that India is not ranking very well in the quantum technology development, including the hardware and algorithm developments. And I'm actually part of a group called India Quantum Group, where there are many researchers who were recently discussing on how many number of patents that is submitted by Indians on quantum algorithms, how many publications from Indians on quantum algorithms. The numbers were pretty disappointing. right? So as a C-DAC being a responsible government institute, we thought we should develop a platform that helps our citizens. It helps our nation to grow in algorithm development or even in the facility to access the various quantum hardware, which is very expensive to access right now, right? We wanted to offer them for free. So this platform to start with will be free. You will get 150 credits as soon as you create an account, right? And if you are from a particular institute, you can just drop an email to me or to my colleague Santosh or anyone that you wanted to have this platform for a little bit of offers or discount for using for your education purpose. We are open to discuss on that particular collaboration as well. And if you want to run it for your corporate training programs, definitely sure, we are ready to discuss on that as well. And beyond 150 qubits, 150 credits, you can actually purchase your credits over here because finally we are dealing with the quantum computers, which are very expensive. And we are looking forward to integrate with number of qubit modalities that exist in the market, including the neutral atoms, including the photonic systems. And finally, there is a bit of expense that is involved for us to take this platform to that level. So we hope that you will understand and support us beyond this 150 credits, purchase some of the credits for your research purpose. And one last request that I have is if you have used Qniverse and if you felt that you like the platform, if it has benefited your research activities, please cite Qniverse in your research papers, and you also can give us a video testimonials or feedback. So with this, I think I will not take much time because we will spend some time in answering the questions as well. So thank you very much for your time and listening to me. If you have any questions, you can ask me. Yeah.
Thank you, Henry. Thanks for that insightful demo and explanation on Qniverse. We have few questions from our participants. Ms. Tejasri, she asked, how are the deprecations in SDK and frequent updates are handled in Qniverse?
Okay, thank you, Tejasvi, for the question. I think that's a very important question that you have asked. And the Qniverse development team, have thought about it. We periodically try to keep the standards. We periodically monitor the developments that is happening in various simulation frameworks and also in the API standards that is offered by the quantum hardware vendors, right? So we periodically keep track of that and we keep developing that. Since Quniverse is being actively used by at least 300 to 400 active users, we schedule an upgradation plan. We schedule the downtime and then we take it for a downtime and then we bring the platform later on with the updated libraries, right? So this way, if you feel that there are few libraries that is out of date, if you feel that there are some libraries that you would require to see in the Qniverse platform, you can very well shoot an email to us and we are happy to integrate them into the platform.
Yeah. The next question is from Ram Nivas. Does it work for CV gates as well?
Okay, I don't have my colleague Dr. Naresh sitting next to me, who is the quantum physicist, who will help us in understanding these things. But right now we have a set of gates, the predominantly used gates in many of the simulation frameworks are supported. But I think this reminds me that I forgot to explain about one of the custom gate creation, right? So we have a unitary gate, which is available in the platform, which will basically allow you to create your own custom gates. So if you feel that there are some gates that are not supported by this platform, you need not be disappointed because this unitary gate, U3 gate, which will allow you to create those custom gates and you have no limitations in creating your own gates, right? So in a way, the question that you are asking is, it should be definitely supported.
The next question is on by Surajit. QSIM and Quniverse are the same.
Okay, I'll be surprised if this question was not asked. QSIM and Qniverse are not same. If you have that opinion, it's not same. That's the right answer. The reason is QSIM is a density matrix simulator. QSIM works only with density matrix simulator, and it does not work with even the state vector simulator, or it does not work with MPS matrix product simulator, or it does not work with a Cirq. It does not work with hardware, right? And the noise models that you are trying to introduce in QSIM, we allow you to introduce various noise parameters like decay, decoherence, and rotation errors, right? It's a pretty good noise parameters that we have in QSIM. But you can play with these noise parameters, you can run them, but your job is not run on a quantum hardware, right? And this platform does not support multiple qubit modalities. It does not work with neutral atoms, it does not work with photonics. But Qniverse is something that tries to bridge that gap. Qniverse offers what QSIM is offering, right? And it offers an umbrella of simulation frameworks, an umbrella of quantum systems in the market, right? So you are using Qniverse and you are dealing with real systems. You are dealing with multiple qubit modalities, right? So they are not same.
The next question is from Arpit Jain. If I am trying to run a Qiskit-based program which requires other Python packages, how to install it as we don't have access to the machine where the program is running internally?
So what's the name? Arpit. Thank you, Arpit. I think this is one thing that I should have addressed during my presentation. Sorry about that. Yes, whatever we offer in the Qniverse platform, it may not have everything. It may not have the algorithms that is required for simulating the nature. It may not have libraries that is required for financial domain. But if you have any such requirements, you can always raise a ticket in our GitHub URL, which you will find in Qniverse platform, and we can get it installed. That is option one. The option two is we are actually having a quantum SDK, which I talked about it in the presentation as well. And this SDK is something that we are going to open it up as an API, right? So tomorrow, you can make use of this SDK and you can include your own libraries and try to submit your jobs to Qniverse platform from your own Visual Studio Code editor or something like that. So these are the two options that is available right now. You can ask us for any library. In fact, we have been receiving many requests in last few months that we need certain libraries for simulating our research problems. So we have made it available for them. So there is, we don't say no to your request, definitely.
The next question is from Swapan. How commercials will be handled when one use IBM quantum machine through Quniverse?
Okay, right now, Qniverse is not very tightly integrated with IBM machines. It means that you don't get unlimited time or for example, let us say you have purchased an API from IBM for a certain number of time, right? You can use that API directly into our platform, and whatever the limit that you get with that API, you can continue using through Qniverse platform. The advantage of using the Qniverse platform, you know that you can have access to multiple hardware. But right now, since I told that it is not tightly integrated, it is pretty loosely integrated through API. So we have 10 minutes of free access that is available for any user. So you just need to input those API keys and you can start using the 10 minutes per month in the IBM platform. We are definitely working on very what I can say, very beneficial model for both the users and as well as the C-DAC, because we have to sustain this platform. So we are working out on a model which will have a pretty good pricing policies so that you can use the IBM systems and any other quantum systems which are commercially available, right?
The next question is by Ashray Jain. Can you tell us more about photonics computing and how is this different?
Okay, I don't know whether we can compare Qniverse with photonics. It's not the right comparison. Qniverse supports multiple qubit architecture, including photonics, right? But I can probably answer this question as what is the difference between the other qubit modalities and photonics quantum computer, right? Generally, for example, let's start with Qniverse, where you created a sample circuits, we created sample qubits, we created some sample gates, right? So we have programmatically created these quantum circuits, right? Now, when I want to physically implement these qubits, right, there are two different approaches. One is a matter-based approach, another one is the light-based approach. Matter-based approach is what making use of atoms, for example, a superconducting system, which actually creates an artificial atom where you manipulate these atoms to perform a quantum operation, right? But in the photonic system, you will make use of a light particle, which is a photon, and you manipulate these photons for performing a computational purpose. So ideally, these two are using a different quantum particle for implementing the quantum phenomena, right? And they have multiple approaches. The superconducting system is a huge machine, which also requires a specialized conditions for working. It can work or it can perform well only if it is the quantum processor is cooled to a temperature that is cooler than the outer space, right? It is in minus 273 degrees Celsius. We call it in millikelvin, right? But photonics is something that can work in the room temperature. So there are pretty good advantages and disadvantages of these two qubit modalities. And both of these systems have promises to solve multiple problems, including the molecular modeling or optimization problems. The one advantage that I see with the photonics is photonics plays a key role in quantum communication, right? So that's the difference between these two architectures. Like Qniverse, I was explaining, it supports photonics as well, but not in this particular version. You will get it in the next version of maybe in 2 months down the line, right?
Yeah, thanks. Thank you, Henry. Thanks for answering to all those questions. Uh, at the interest of time, we will take the questions which have been posted by other participants and will be answered through our Zulip forum platform. And some of the announcements I have. We will be having one intermediate course on next Monday, again 4 to 5 p.m., which will be announced through email to cover up the basics of quantum computing gates and other principles. And for next two session, we have speakers from JP Institutes called Professor Anirban Patak and another speaker from IIT Roorkee, who is Jyotirman and Jyotishwaran. And one more speaker we have for the next other week, which is from Calcutta University called Professor Ramlan. So this is for the information.
I will answer one question. Okay, so while Santosh was concluding, I briefly saw a question which is asked by Adam Ahmed, who is asking some interesting questions that I think I should have again answered or presented in my presentation itself. For Qniverse, is the free credits amount for lifetime or will it get refreshed periodically? Right now it is 150 credits. If you have, it means that it's a lifetime credit. But we are also considering how we can continue supporting the free version of Qniverse as well. So we will work out on that model and we'll let you know. What is the maximum number of qubits which we can simulate? Yeah. So I told you that there are multiple simulation frameworks that we are supporting. So you can simulate 35 qubits using GPU and Qiskit simulation backends. And if there are simulators which is called as QLAX and Quest, which can simulate up to 40 qubits, right? Because we are simulating it on a high performance systems. So you have the advantage of few more extra qubits that you can use for your research. Is there a doc for QML in Qniverse so that I can learn and try out things? Yes, I think my colleague Raja Singh says yes. It is available in the documentation page. You can go there and explore it. And we also have some preloaded algorithms that are very specific to QML, QSVM and QPE, and then clustering algorithms, k-means algorithms, right? So you can get started with those algorithms, and definitely we are keep loading many algorithms. Every release is going to have at least minimum of 3 to 4 additional algorithms that is loaded. So these are the questions that I thought I will explain so that it benefits everyone. Thank you very much. Thanks for your time. Over to Santosh.
Yeah, thank you, Henry. Thanks for answering to that last question. As I said, on Monday we will have an intermediate course which explains the basics of qubits and the gates. What are the gates, the matrices, and the math involved in that, so that it will be beneficial, when you move forward with the algorithm. So it will help you in understanding it better. And as I said, we have next speakers, which you can see it in our Quniverse website, quniverse.in. There is a webinar section on the top menu. You can navigate and you can find our next speakers. And we will be posting few questions, the quizzes in Zulip platform. Please do take time and answer those questions. So this is for this week. Thank you all for joining us to this week 2 on introduction to Qniverse. Thank you, and hope to see you back on Monday. Thank you all.